Yeah, hello everyone. It's our pleasure to have Elias here to share about his work. With titles Understanding QML also require rethinking generalizations. And I think that is kind of an important work for everyone to know about, especially for those who work on theoretical analysis of generalization errors of QML models. I think Elias will be able to tell us more about it, and the floor is yours. Yes. Oops. Maybe we have lost Elias.
Sorry, I think my internet blinked a bit.
Right. Yeah. I think you can start now. Just introduce you and
Okay.
yeah. Thanks.
No, thank you. Thanks for the invitation. It's really my pleasure to be here, and I'm I'm very happy to be able to present our recent work. Um, as you could imagine, this work was not done in isolation. It was like a very nice collaboration within Jan Eisert's group here in Berlin, and with Carlos also, who's here in the audience. And depending the questions you have, maybe he can also jump in. This is a bit of an outline for you to have an idea of what awaits you. And first, I spend a bit more time than maybe as usual in setting the right mindset and common grounds for what's the place of this work in the literature. Then, to me, the most important part of this talk will be this thing I call the pitch, which is I'll present the problem and give our results in the most non-technical terms, so that with the easy take-home message format. And so for most of you, if you take something out of this seminar today, I would encourage you to be this part 2. And then for those among you who find these things interesting and who would really like to hear more and the details of and how do these things work, then we have this other this second part where I will talk about uniform generalization bounds, and then how with randomization tests and memorization we can say something interesting about uniform generalization bounds. And then just some closing remarks, and maybe hopefully we'll have some time for questions. And so right away for the introduction, since there are a bunch of different things that can be rightfully called quantum machine learning, I just want to make clear what we're talking about here today. Usually machine learning is somehow of the interplay between a learning model, some data task, and some training algorithm that finds a function within the model to fit the data. And so if you want to talk about quantum machine learning, then you need to make at least one of those 3 things quantum. Today, we will talk about 2 things being quantum. Particular quantum model, meaning we will use quantum circuits to fit data. We'll also have quantum data, meaning we'll have quantum states as inputs instead of just images or real vectors. And then we'll stick with classical training algorithms like gradient descent using parameter shift rules and this sort of things. So quantum model, quantum data, classical training algorithm. And the point from where we start is this statement that if you've read the introduction of papers recently, usually these parameterized quantum circuits are presented as a possible important application for near-term quantum devices in solving tasks using data. So you have a few data examples, you want to train some function according to these examples, and then you want this to solve some big task. And then the goal would be to find some practical important task like self-driving cars or protein folding or this sort of things, and solve it with parameterized quantum circuits in a way that's faster or better in some sense than classical machine learning or classical computation possibilities. We're not quite there yet. It seems hard to prove this, mathematically proves that with parameterized quantum circuits, we can find quantum advantage in real world practical data. So instead, what we do is just study parameterized quantum circuits as learning models from a holistic perspective. And here, usually, you divide the studies into 3 big branches. And expressivity, which is what sort of functions can this circuit represent. Trainability is, okay, if I set up some gradient descent, will it ever converge and finish somewhere? And generalization is more okay, I have a model, I have some training examples. Now, how will the performance of this model on these training examples relate to like performance in the whole spectrum of data? And the third one is the one we're talking about today, and it's actually super important because the whole point of machine learning is to somehow be able to, using a few examples, be able to extrapolate information to things you haven't seen before. And so what we do here is first like train a learning model with limited data, and then we're interested to know, okay, but how will this model perform further than the data we train on? And like some clear, like, visceral examples is like, for example, with self-driving cars. Surely, if you're teaching a car how to drive, then you want this car to not kill people. And it's very nice if a car doesn't kill people while it's learning how to drive. But once it's learned how to drive, you would also like that the car, once you deploy it and put it in Silicon Valley, the streets of San Francisco, then that they will also not kill people then. And this is like a clear example of generalization, whether a self-driving car killed people during training or after training, and whether it kills people once it's out there, would be like good generalization, no killing, and bad generalization, then you could have some trouble. So it's like a very, very important problem, and it's like you need good generalization in order to have successful machine learning, be it classical or quantum. Now I give a tiny bit of context of like historical perspectives on the field. This field of like the mathematics of learning starts in the 70s with Vapnik and others. And there, and for many decades, they established this traditional learning theory. They started talking about generalization bounds, which is something I'll introduce in a bit. And like throughout this time, like the theory was developed, new theorems were proven, and the things were applied to the learning models of the time. Like, for example, first kernel methods or neural networks, and then deep neural networks. Then fast forward 2016, there was this paper by some people at DeepMind whose message was clear. It was like this traditional learning theory approach that came from the 70s cannot explain the success of deep learning. Like deep learning is successful and we know it. We have this theory that predicts what machine learning does, and this theory cannot explain the success of the experiments we see. From then on, in classical machine learning, this has been some sort of revolution where like a new approach to generalization has been developed and used. But in parallel, in the last few years, for quantum machine learning, the theory and like the approach to study generalization in particular has followed the steps of the traditional learning theory, the one that was used many decades ago, and which was seen not to work for deep learning. Our paper today that kind of closes this circle, and our statement, which I will explain slowly, is that this old traditional learning theory also cannot explain the success of current quantum machine learning models. And this is kind of a fundamental statement, if you ask me, because we said that there is no successful machine learning without generalization. And then the question really becomes how do we study generalization? And for many years, we've been like, for many years now, like since the early 2020s, we've been studying it in a way, but we were aware of this like results from classical machine learning, where for big classical models, the traditional theory wouldn't work. And we kind of told ourselves or believed that maybe for small quantum models, we can actually get away with the traditional theory. But there was always like the question, is this really true? Should we be doing something different? And then like as a closing of this section, the big question here is, if I want to look at parameterized quantum circuits as quantum machine learning models, the thing I care about today is how well do they generalize? Like in general, is this thing like, is parameterized quantum circuits as a concept a good learning model in terms of generalization? And there was this paper recently by Matthias Caro, some people at Los Alamos, which said, yes, PQCs can actually generalize pretty good. And they look at many different scenarios using PQCs, and they look at the theory, like they prove some generalization bounds, but importantly for us, they also run experiments where quantum circuits of relatively small size, like current scale, near-term quantum circuits, actually had surprisingly good generalization performance. Like if you haven't read this paper, I recommend you all to read it. So we have that small quantum models can generalize properly, and we ask ourselves, okay, where in all of this, where does the theory fit? With this, start like the pitch, so like the thing I would like you to take home from the seminar today. And from this, we start with a problem definition. And in particular, I've been mentioning machine learning, but we focus on supervised learning, where we have a data distribution, D, that's like over inputs, that could be images or quantum states, and labels, that would be like real numbers, for example. And it's important that this distribution is supposed to be unknown but fixed. And what does it mean, unknown but fixed? You can imagine that like this distribution is actually me, Elias, with my phone. The X, like the set of images, is just like 128 times 128 RGB pixels. And the labels are just, is this an image of a cat or a dog? Now, I can go on the street and just take pictures of cats and dogs. And arguably, you could say that there exists a formula that relates the color of each pixel at every step, at every picture I take, and whether the image corresponded to a cat or a dog. But the kind of writing down this formula, this Elias distribution formula, would be super, super hard. Like a priori, we have to assume we could not write it down. But at the same time, this distribution exists, like it's me, like, and it's always me. And if I go on the street and I take pictures of cats and dogs, then this is like a well-defined thing. But yeah, so like this is how we typically think of like these machine learning problems. Then we try to fit this data distribution using some function family, sometimes also called hypothesis family or hypothesis class, which is just functions that take inputs and produce labels. And this function family like is a set where the functions are parameterized by some parameters theta. And so if we vary all those thetas, then we obtain different functions. In particular, this could be understood as parameterized quantum circuits with fixed architecture, and like where the only thing you do is change the rotation angles, or neural networks with fixed structure, where you only change the biases and weights. And finally, we have like this performance, like this way of quantifying performance called the population risk, which is just some number that takes a function and computes like the average quality over the entire data distribution and produces a number. If the number is small, it means the performance was good and we're in business. If this number is large, then it means like this function was not a very good solution for this data distribution. So ideally, we have the data distribution on one side, the hypothesis class on the other side, and together we would like to obtain a function that minimizes this population risk over the data distribution. So this would be like the important goal here. So that's what we want. We want to find a population risk minimizer. The problem is that we cannot do that because in order to find such a thing, we would need access to the D distribution. And we assume that this distribution was unknown. So like we really cannot obtain this thing we want. Instead, what we could do is like produce a training set, like obtain capital N many samples from the distribution, and then use a proxy for the performance. Instead of looking at the population risk, so on the entire distribution, we can look at the performance only on the training set. And this is this R hat, like the difference between R hat and R no hat. And this is that R, like regular R uses the entire distribution, and R hat uses only some finite training set. But the idea is the same. Like we just get the average performance over the data we have. And if we get a small number, that's good. If we get a big number, that's not good. And what we can do with this, because we have access to S and to R hat, is we in principle can assume that we could obtain a function that minimizes this empirical risk for a given training set. But that's not what we want. What we want is a population risk minimizer. So even if we could do all of this and we could obtain this F star, which minimizes the empirical risk, the question would be, what is the true population risk of this function that we obtained? And this is like the big notion that we need to define today, which is called the generalization gap. The generalization gap of a function is really just the difference between the training performance or empirical risk and the true performance, the population risk. If this number is small, it means that whatever we obtained for training will be similar in for the whole task. And in particular, if we find a function that fits the training data perfectly and somehow we have reasons to believe that the generalization gap has to be small, then that means that the entire, the performance on the entire data distribution will also be good, which would be great. And just in case some among you in the audience are more visual people than just bullet point people, I make it like a teeny tiny visualization. We have the data distribution D. From it, we produce a training set of capital N many points. We fit this thing to a learning algorithm that searches through our hypothesis class, which could be like parameters quantum circuits, and just finds the best parameters, and produces this approximate empirical risk minimizer. Produces a function that achieves the best performance on the training set. From this, it follows that the empirical risk of this function is small because it's a minimum. And then what we ask ourselves is, okay, but if I use the whole distribution again, would the performance be good still? And this is the thing I'm defining right now. Like the difference between the training performance and the true performance is what I'll call the generalization gap. And in this traditional approach to learning theory, what you do is you look at the generalization gap, which now I color-coded because the names are similar, but they're different things. Look at the generalization gap and try to come up with an upper bound, like something that must hold, which I write in blue, and it's like this generalization bound. So generalization bound is a function that takes an element from your hypothesis class and also produces a number. And the idea is that you want to find such functions which in some specific case of a learning task, of a learning problem, you can guarantee that the generalization gap of one of your functions, in particular, you would care about the empirical risk minimizers, will be at most as large as the value of this function. Now, this is a very general thing, and a priori, if you had to come up with this thing, you could make it depend on many different things that make sense. So like, depending on the properties of F, this number could change. If you had some information on the loss landscape, or like when you did gradient descent, then you would ideally try to use that information. Maybe if you use Adam instead of SGD, you know that you will converge to different types of functions, and that should also be taken into account. Or maybe if you know that your data is very spiked in some way, or if you use more or less training samples, like all of these things reasonably should be taken into account when trying to find this thing. But in particular, like in practice, this is a quite difficult task. Like really proving an upper bound that holds for a relevant learning task is very like mathematically intense, people say. And so what we do is we always look at restricted cases of this thing. And to this I'll come later about these restricted cases. But now let me kind of say what we want to say in this paper. On the one hand, we have that empirically, people have run experiments that have seen that PQCs can have good generalization, like meaning they can have a small generalization gap. In parallel, there are many papers that prove some upper bounds for what the generalization gap of a PQC can be. And then this really leads to the natural question, can the theory explain the experiments? Or said otherwise, can our generalization bounds explain the good generalization of PQCs? And what we say today, like this is the message, is no, they cannot. And I will explain why, but like this is the message. But what do we mean that with this statement? Like in practice, in the quantum machine learning theory, we always use something called uniform generalization bounds, which I introduce in a second. And like one way of saying what I've already said is that in the experiments, we found that the generalization gap of PQCs is small, not to confuse with generalization bound. And what we do is we look at the cases where the generalization gap has been reported to be small, and then we prove that in those cases, every uniform generalization bound, so in the literature, there are many different bounds proved, we say that every and all of them have to be loose or large. And in a way, what we're saying is that we find that the generalization gap is small. We find that the uniform generalization bound is lower bounded by a large number. So like this bound is loose in a way. Like there's a big distance between the number that we obtain if we run an experiment and the bound that we obtain from predicting with math. And this is like the take-home message. Like the theory cannot explain the generalization that we found, and this is the reason why, or this is the way in which we mean it. Okay, and now let me take the details of this thing. So let's look at uniform generalization bounds. As I said, this in the traditional learning theory approach, the thing that was started in the 70s and that in classical machine learning was used until the 2010s, and which we have been doing for quantum machine learning in the last 4 or 5 years. The first thing you do is you look at all the long list of things I said the generalization bound could depend on, and you fix yourself on 2. You say, and this is what you call uniform. You will try to prove uniform. You will try to prove a generalization bound, whose value depends only on structural properties of your function family, and on the number of training samples. This might seem a bit constructed, but in the literature, it's the most common thing. Like this is the mainstream. In particular, the structural properties are captured by something called complexity measure. And today, I will not go deeply into what complexity measures are or how they look. If you would like, you can ask me more about it. But like this is something that's a bit confusing to just drop. Like people who know will already know, and people who don't know will potentially, I will not be able to explain it in a nice way. So you can ask me more about this, or otherwise you can check any of the papers, and they make a very good job explaining them. Okay, number of training samples is pretty clear, like how many data points you had to start with. Whereas the structural properties could be many different things. And here is a selection of like papers that have been coming out since 2020. And some different structural properties they look at are like very tangible things, like number of trainable gates of your circuit, or like for this data reuploading with classical data, the size of the Fourier spectrum of the trigonometric polynomial that corresponds to your circuit, or really just something as easy as the number of trainable parameters, or more like quantum things, like the amount of magic in your circuits seen as channels. And these are like less than half of all the papers that have been proved on these things. So it's really a thing, like people care about this. And we make the point that all of those theorems fit this one template that I'll present now. So it's a template for uniform generalization bounds. So the thing that each of those theorems fixes is the data space, the hypothesis family they consider, the population risk, which means like what loss function they look at, and what complexity measure they will care about. And then those theorems apply for any data distribution. So like each theorem you don't get to fix this thing. This has to hold for every data distribution and for any training set of size n sampled IID from the data distribution, which also gives you the corresponding empirical risk. Then all of those papers contain a theorem of this type. The generalization bound, so the thing that bounds the generalization gap, has to hold for any function in the hypothesis class. And in particular, it's something that's like polynomially, like that depends polynomially in the complexity measure, and 1/square root in the number of training points, usually. So these theorems say there's a learning task. If you fix all of the things, then there's a guarantee that the generalization gap, so the difference between the training error and the test error that you would obtain, has to be upper bounded by this number. And they give like the formula for this number. And these things are called uniform because they hold for any hypothesis in the family, and most importantly, for any data distribution. And this is great. Like if you have a uniform generalization bound that works, let's say, then you don't even need to train your model to know how well it will generalize, because whatever you do, it will work for all hypotheses, like the ones that you obtain from training and the ones that you don't obtain for training, and for any data distribution. So like, regardless what your problem is, this thing will work. And if you do this, then you can guide what model you want to use to solve your learning task. And that's pretty powerful. But now let's do a little thought experiment to see that uniform generalization bounds might not be the best. Imagine there's a data distribution that corresponds to like cats and dogs, for which learning is impossible. How could that be? Like imagine I take pictures of cats and dogs, but instead of telling you this is a cat, this is a dog, every time I take a picture, I also flip a coin. And if it's heads, I say this is a cat. If it's tails, I say this is a dog. And that's it. Then arguably, whatever you do, you cannot do better than random guessing. So the population risk of any function that tries to solve this task has to be large. Like the true performance has to be bad. But if we approach this in the supervised learning sense, we would first sample a training set from this corrupt distribution, and we call it the corrupt training set. And then there's like a two-step thing. If we find a function that fits this training set, then by necessity, the generalization gap has to be large, because the difference between the true between the population risk, which we said is large, and the empirical risk, which we said is small, has to be large. And if we prove that the generalization gap has to be large, then it kind of doesn't matter what the bound says, because the generalization gap is large. So the simplified message that I'll be reiterating is that if you find a hypothesis within your class that can fit a corrupt training set, then any uniform generalization bound has to also be large for that class. And I put it like alone in the slide because it's very important and it will appear again. I say it again. If a hypothesis class can fit corrupt training sets, then any uniform generalization bound for that class and that problem has to be large. And if a generalization bound is large, then it's kind of telling us that it's not giving any information. And so it's not a good bound. And this is good to keep in mind. I'll be repeating it. And with this, we look at how to produce these corrupt data distributions and how to find hypotheses that fit corrupt training sets. To make this clear, I start with a classical data example. I just went online and found some images from the CIFAR 10 set, which like images have to be classified in different classes. Like I took some images of cats and dogs, and a well-posed machine learning problem would be given these inputs, produce label cat for the cats, and label dog for the dogs. And this is what we would call real data. One way in which we could corrupt this is now look at, like, go to every image and just flip a 7-sided coin and just like assign labels uniformly at random to each image. So now, like I put in red the images that don't correspond to the true label, and in blue the ones that still do. Of course, some of them might still fall in the right place, but many of them won't. And this kind of explains, like, even if you have your best neural network in the world, if you're trying to solve this task where the labels are not correlated with the images, then after training, your function will be as good as just random guessing, as assigning the same class for every image. Hope this is intuitive enough. Then another thing we can do is just do partially corrupted labels, which means we, for every image with a certain probability, we give a random label, and with a certain probability, we keep the true label. And this is interesting to see if a model can fit signal and noise at the same time. And another thing, which is also interesting, is just keep the labels untouched and just change the images. As like in this case, replace them with Gaussian white noise. And this is interesting because if you look at Gaussian white noise, like the local structure of the image is kind of gone. So the way in which convolutional neural networks and convolutional quantum neural networks work kind of breaks down if you look at this random states, we call them, because for us it will be quantum states. Okay, with this picture in mind, what we'll do is kind of the same idea, but instead of images, we will have quantum states, and instead of cats and dogs, we will have quantum phases, and I explain this in a second. But this is now what's on screen is like our main framework, which kind of explains the whole logic. And there's a lot to take in, so let me unpack and go step by step. There are two boxes, empirical experiments and uniform generalization bounds. We start from empirical experiments in the top half. We have our original data distribution, which in this case will be some quantum states that I represent as some spins and some labels. We produce a quote unquote small training set and we give it to a training algorithm that within our class of quantum circuits finds a hypothesis called F original, which finds which can fit the training set nicely, which means it finds a small training error. Now, once we have this, independently of all this training, now we sample we sample again from the data distribution a large test set, and if we have the test set to be much larger than the training set, this works nicely. And we just ask ourselves, okay, what's the performance of this function on the test set? And empirically, we run these things and we find that the test set is also small for the original data distribution. This is great. We trained, we found a small training set, we tested, we found a small test set. So in total, we have that the generalization gap of this model is small. And this is what makes us say that this parameterized quantum circuits can generalize nicely. Now, once we have this, we do this randomization or corruption, and we get a new data distribution, which now is the one that I say is corrupt. And we do the exact same thing. We sample a small training set of the same size as before. We fit it to the learning algorithm for the same hypothesis class as before, and now we obtain a potentially different function. And this different function, because we found it by training by fitting the training set, will reach potentially a small training error. And now again, we just sample again a large test set and we look at the performance of this new function on the test set. But because this new data distribution was randomized, then by necessity, almost like by construction, the test error achieved by this function has to be large, just because the test error of every function has to be large in these randomized versions where the inputs and labels hold no relationship. Now, if we have a small number and a large number, and we look at the magnitude of the difference, then we obtain a large number, which makes us say, for this contrived experiment with random data, where things were corrupted, the generalization gap we obtain is large. But notice that the only thing that we changed between the true data distribution and the corrupted data distribution was the data distribution. Like the size of the training set was the same, the hypothesis family we used was the same, the learning algorithm we used was the same, everything was the same. We only changed the data distribution. And now if we go to box B, uniform generalization bounds, we read the papers in quantum machine learning, and we see that these uniform generalization bounds tell us that every function in this family has to fulfill this thing, that the generalization gap has to be smaller than this function, independently of the data distribution. So this upper bound is an upper bound that works both for the true case, like for the original case, and for the corrupted case, which leads us to like prove that the bound is large, because we found an example where the left-hand side was large, which means that the right-hand side must also be large because it's a bound. And this is like the big, nice message of our paper, I would say. Now, I bring again the simplified message. We said that if a hypothesis class can fit corrupt training sets, then uniform generalization bounds must be large. And now you maybe understand better what I meant with this. But then there's a disclaimer, because this might not work always. Like if we keep making the training set larger and larger, then at some point our function will not, like our hypothesis family will not be able to find a small training error. And so at some point the training error of F corrupted would have to start being large. And then once the training error starts growing, because the test error has to stay constant because it's as big as it gets, then at some point, eventually, if we have enough training samples, then we could reach a small generalization gap. And that's kind of in agreement with the math. Like this is what the theorems say. It's just that in practice, in the cases where we care, where we have like the right number of training points for the original data set to be solved easily, it just happens that we could find that this was the case. But yeah, like this was just a mini explanation that we're not saying that the theorems are wrong. We're just saying that in some sense they don't apply in, like that the bounds are loose for practically relevant problems. Okay, up until now, we've been talking a lot about like arbitrary, like about abstract learning tasks and learning models and data distributions. And now I just explained briefly what our learning task and our model is. Our learning task is quantum phase recognition, and our model is the QCNN that I explained in the next slide. So the learning task is we're given ground states of this generalized cluster Hamiltonian, and we want to classify them according to their phase. This is the Hamiltonian. It's just sum of 1, 2, and 3 body terms. And we know, like in the theory, we know that if we look at the different J1 and J2 coupling strengths, the ground states of this Hamiltonian correspond to one of 4 different symmetry protected, one of 4 different quantum phases that we just label 1, 2, 3, 4. And the idea is we're given, like we sample G1 and G2 randomly, we prepare the corresponding quantum state, and then we want to find a function that tells us which of the 4 phases this was it. This is a very relevant problem in quantum many-body physics, and it's one of those things that people say / believes that quantum machine learning could be good for. So this is the learning task. And the model is this thing called the quantum convolutional neural network, which was proposed by Iris Kong in Michael Lukin's group. And it looks a bit like this. This is the model we use, and it's inspired in classical deep learning, where you have an interleaving of convolutional layers and pooling layers. In convolutional layers, what you do is kind of apply a translation invariant map that acts as a filter classically, and that's why it has parameter sharing. And after that, you do some sort of feature extraction, where after you apply this translation invariant map, you do some measurements on a constant ratio of your qubits, and then only a few of them survive to the next layer, where you again do some translation invariant thing, and then also do some dimensionality reduction until at the end you measure something easy. Because it has this local intermediate measurements, this thing is very good in using local information, like local correlations in the quantum state, which is analogous to the case of classical neural networks. And a nice thing about this is that it was found that because it's so small, it doesn't have barren plateaus, while it's still not necessarily classically simulatable if the input state is very entangled. So this is the model. This is what we call the quantum convolutional neural network. And it's very trendy at the time because so far it only has good things. Okay. In our numerical experiments, the thing we do is very simple. We first corrupt the data distribution and then train. This is distribution of ground states now. And basically what we're looking for is if the training error is small, then the uniform generalization bounds are large. We do this for 3 different randomizations. And we also look a bit separately at this case of partially corrupted labels, but all within the same framework. First plot, we look at the random labels, random states, and real data versions. In this graph, we have different training set sizes. So the larger the training set, the smaller the generalization gap should be. On the y-axis, we have the generalization gap, which is already the difference between training error and test error. And these numbers are averages over experiments using up to 32 qubits. And and we know that for the random labels and random states case, the test error must always be large. And because the ratio of different classes is a bit different, the maximum distance that we can achieve is like the maximum generalization gap is slightly different, but it plays the same role. So in the blue and orange cases, we find perfect training error. So the training error would be down here. And the test error is as bad as possible. So it's like the equivalent of random guessing. And for the real data, we see that as we grow the number of points, the generalization gap gets smaller, also because the training error gets higher. But in any case, we see that the generalization gap for the randomized cases is very, very large, which means that the training error is very, very small. So the message of this first experiment is that the QCNN can fit random distributions of either random states or random labels. In this case, for like 20 points, we see that the generalization gap starts to decay, both for the random and the original data. But this is because the training, like the model struggles with fitting the training error perfectly. So we see that the training accuracy starts to drop, but both for the original and the random experiments in the same way. Second experiment, now we look only at this partially corrupted data. So in the x-axis, we have label corruption. Here we have like the original data, no corruption. And here we have full corruption, like every point is given a random class. In this experiment, we focus on n qubit because we wanted to look at cases where the training error is always 0. And this is the thing we could guarantee. And we look at 3 different training sample sizes. But in all of these things, we observe that at the start, like for 0 corruption, the test error is very small, and it grows kind of linearly, which means until it reaches the performance of random guessing, which means that this that the QCNN is able to fit the signal in the data while it still also memorizes the noise, because in all of these cases the training error is 0, but not in all of these cases the test error is not as large as it can be, so that the QCNN is able to fit some of it. And here in the inset, this is interesting. We plot the time it took to convergence, and we have it for 4 different label corruptions, and we see that blue and pink are the ones that take the shortest time. And it's interesting that blue and pink are the 0 corruption and the full corruption. So somehow it's easier in a way to fit completely corrupted data than only partially corrupted data. And yeah, this is just an interesting thing in itself. So, but yeah, this is the message. The QCNN is able to fit noise, so memorize noise while still fitting the remaining signal. One more time, the simplified message. If a hypothesis class can fit a corrupt training set, then uniform generalization bounds are too large for that class. What we find in our experiments is precisely that the QCNN, so existing QML models, can accurately fit random labels, fit random states, and fit partially corrupted labels. So what comes out of these experiments is that all uniform generalization bounds have to be large for this class of existing quantum machine learning models. So for the QCNN, for this number of training sets. We're approaching the end. In this 5th part, I will just give an idea of our theoretical results, which pair nicely with the experiments, and then we're done. But just to reinforce the message, the simplified message, again, this is really the core of all of this. If we can find a hypothesis class that fits corrupt training sets, then we prove that uniform generalization bounds kind of don't work. And to this, I put a follow-up, which is, if we can fit any labeled training set, then in particular, we can also fit corrupt ones. So this goes in the direction of memorization. What I call memorization memorization is the capacity or ability of a hypothesis class. Say that a hypothesis class can memorize if it can fit any labeled set of any size, everything. Because in machine learning, we always deal with finite training sets, then the relevant thing for us is this finite sample exclusivity, which is kind of saying it's memorization, but on finite fixed number of data. And this was already in this classical paper by DeepMind, and it's kind of an important concept here. And so I show you now 2 theorems. Gladly, you can ask me more about them, because here is just the informal zoomed out perspective. But yeah, this theorem 1 deals about the finite sample exclusivity of quantum circuits. So without limiting to parameterized quantum circuits or something that looks like quantum machine learning. And what we say is that if you give us n quantum states on capital N quantum states on lowercase n qubits, where you have a reasonable number of them, then for any labeling of those states, we can always construct a circuit of polynomial depth, which realizes this labeling. So that f of each of the rows equals each of the y's. So this proves that for capital N many quantum states, quantum circuits are universal, which might be not so surprising. But now we put in the limitation that PQCs are, that the limitation for finite sample exclusivity of PQCs. And here we have, again, given states on so many qubits and a reasonable number of them. And now we need to add some distinguishability condition. Then we can construct a PQC, so not just any quantum circuit, but something that depends on 1 qubit trainable gates and, sorry, on a few trainable gates. Sorry. If we have these quantum states, then we prove that we can construct a parameterized quantum circuit like the ones you have at home that looks like m of theta. So for different thetas, it's a different circuit, such that after we've constructed this PQC, we can fix any vector of real labels, and then we can find the corresponding parameters to fit those data perfectly. So the difference with respect to theorem 1 is that now we have to add this stronger distinguishability condition, and now we have something that looks like a PQC. And because all this time we talked about QML as thinking of PQCs, this is like an important thing. So the conclusion, like the message from our theoretical results, is that we ran experiments on up to 32 qubits, which is kind of a lot for these quantum machine learning tasks, but it's not 3 trillion qubits. And with these theorems, what we're saying is that there is sufficient conditions and a clear mechanism for how PQCs of arbitrary size could fit a big number of points. So like this memorization thing could happen to arbitrary sizes, and this says that uniform generalization bounds should also break at sizes bigger than the ones we tried in our experiments. And now just briefly, the summary and outlook of our work. What we said today, the take-home message from the beginning was that uniform generalization bounds cannot explain the good generalization performance we see in existing quantum machine learning models. And because the QCNN ansatz is so limited, it kind of implies that less limited ansätze are also affected by our results. You can ask me more about this if you want. An interesting thing is that when we run the experiments with corrupted data and with the original labels, the learning dynamics seem to be the same. Like the QCNN kind of doesn't care if what it's fitting is noise or true data. And I would like as a closing note to extend an invitation to everyone, because what's happened is we have all of this literature on uniform generalization bounds. And what we're saying is that uniform generalization bounds seem not to be a good thing. So everyone, please feel encouraged to join our field, come work with us in trying to prove new non-uniform generalization bounds, which can predict the good generalization behavior we see already for the QCNN, for example. And precisely in this vein, I give like 2 possible lines of how this could come about. And the clear thing to do is we said that these things have been known in the classical literature for a while, and there have been papers and applications of those things. So you could just go and follow what the literature in classical machine learning has been. Or another potentially interesting is, instead of just applying the classical tools, like the classical hammers, and trying to hit this quantum nail, we could try to come up with a quantum hammer, like come up with some approach to learning theory that uses genuinely quantum complexity measures or quantities. And here, like, this is an easy thing to say because I have no idea how that would ever look like, but it's an interesting thought to entertain. And with this, I would like to thank you all for your attention. Sorry that I was a tiny bit above time, and I'll be very excited to answer your questions, if any. Thank you.
Yeah, thank Elias for the very interesting talk, and I really liked the way that you emphasize this simplified messages. If I'm not wrong, you emphasize it 4 times, so I think this is really easy to kind of like remembers like the take-home message of TikTok. For the audience, if you have any questions, feel free to type it out in the chat or unmute yourself. And while they are thinking about the question, maybe I could like ask about some question first.
Yes, please.
So over here, like I saw you focusing on like the small data regimes, right? While in the classical papers, when I'm reading it, they are like normally focusing on like deep neural network, deep learnings with like a lot of like training and testing data. So it seems that the framework is a bit different, and why do you think that you will be working here? And the other follow-up questions would be, over here you are considering a very small number of training data, right? So how would you differentiate the phenomenon that you're describing with the finite side effect, because we know for machine learning model, when we have access to like very small number of data sets, right, and then it tend to overfit the training data and performing like worse for the testing data.
Yeah, I think so. Thank you for those questions. Those are fantastic questions because they hit exactly on the right points. And I have to say, it took me like quite some time to make my mind around this. The first thing you said, which is very important, is that if you look at the specifics of the experiments we run and the experiments in this classical paper, a couple of things look very differently. And the first thing that looks very differently is the number of training points and the size of the models we use. And that's why at the beginning, when I gave the like historic account, I said that in the classical paper, they said the message is that traditional learning theory does not apply to deep learning. And this leaves the door open to the traditional approach to working for like small neural networks. And this was not studied in that paper, but a priori it could be. So they proved that for this gigantic convolutional neural networks with billions of parameters, then they could memorize whatever you want. And this says that the traditional, like the uniform generalization bounds, don't work for big classical models. And this was known to the authors of all of these papers in quantum machine learning recently. So why did they write those papers if that was the case? And the thing is, in the classical paper, they say that this is the case for big models, whereas nowadays in variational quantum machine learning, we have this NISQ limitation. So everything we do is kind of small. And big models have more capacity than small models. So just because big models can memorize things, that doesn't mean that small models could also memorize things. So it could have well been the case, and this was a bit like the elephant in the room that I was saying before, that for small models, the traditional approach still works. And like for the small PQCs or like, for this small QCNNs, it could have been that the model capacity is too small and this hypothesis class cannot fit the random data. And what we kind of say is that this is not the case. So one of the differences between our paper and the paper by DeepMind is that we show that uniform generalization bounds are like the wrong approach already for small scale quantum machine learning. So there's really nothing, it seems that there's really nothing to gain from like this uniform generalization bounds for quantum machine learning at any interesting regime. And that was point number one. Point number two is in some way, and the classical paper looked at the state of the art in classical machine learning of the time. They looked at models that had very good generalization performance. And then they just said, okay, for these models, which we find interesting because they can generalize, we prove that our explanations of generalization are bad. But they start from this thing that they start from the observation that those models are interesting because they solve a task. And this is actually similar to us. We look at, again, at this paper by Matthias Caro called like generalization from few data in quantum machine learning or something. And they see that this small QCNN solves tasks with very good generalization. So they see that this very small model, if you give it a very few training examples, then it generalizes properly. So in terms of purely generalization performance, this kind of sets the state of the art for quantum machine learning, because we don't have like these benchmarks, but like if you just go at the papers and see how good models perform, this is the smallest model that solves a non-trivial task in a good way, like with a few training points, it extrapolates to the whole thing. So that's precisely our starting point. We start from the observation there are these quantum models that solve a task and do good generalization. And it just happens to be small models, but it could have been anything. And we say that our explanations of generalization fail for this interesting case where we have seen good generalization. Maybe it's a
Right.
bit of a subtle point, but Like these two things are like, on the one hand, it's just the best we have until now is what we looked at. And the other thing is, yeah, like the classical paper didn't talk about small models at all.
Right.
We're
So I
waiting.
think like we can also like repeat this kind of task like when we have access to like large scale models, and then we can kind of verify whether it's like this kind of extrapolation is also true or not in quantum neural networks or quantum machine learning models in general. Yeah.
Yeah, and the good thing is that a small model, all of this comes down to the model capacity. If one model is more expressive than another model, then their memorization ability will be better. So if we prove that small models can memorize, this is like in the conclusion, sorry. If we prove that small models can memorize, then it follows that big models can also memorize. And if we prove that the QCNN can memorize, the QCNN has parameter sharing, logarithmic depth, and intermediate measurements. If we drop these restrictions, we end up with a hardware efficient ansatz, which contains the QCNN. So the hardware efficient ansatz has a larger model capacity than the QCNN. So because the QCNN can memorize, then the hardware efficient ansatz can also memorize. So all variational quantum machine learning models and ansätze can memorize at the current scale. And that implies that they will also be able to memorize at a bigger scale. So our experiments kind of have very long reach in that they rule out that the generalization bounds work for bigger models in general.
So the second question that I asked just now, actually we do have one question from the audience, but maybe let me ask the second question first. Because you are considering small data sets, right? How do you differentiate the phenomenon that you like kind of like propose in your schemes with the finite size effect? Because we know that when we have access to limited amount of data sets, right? It tend to overfit on the training data while kind of performing worse for the second one.
Yeah, sorry, that's also a very good question. And my answer will not be super satisfying because this is a problem we don't address. So on a meta level, we're not trying to explain why the models can generalize. We're only saying that our explanations up until now were bad. And indeed, so in a way, if a model overfits, that doesn't mean that the model will not generalize. Like you can look at classical machine learning for this. And you raised a very interesting point of, okay, but how can we distinguish between models which overfit and generalize and models which overfit and don't generalize? And to this, I do not have an answer. And it's also not what we were trying to answer here.
Okay.
And to me, it sounds like a very, very hard question. Like we don't know this for classical machine learning either.
Right. It's basically a very big questions that just waiting for people to go and tackle and answer that. Right.
Yes, exactly.
Okay.
Feel
So
invited.
yep. Yeah, let me kind of like look at what questions the audience asked. So we have one question from Supanat. Hey, Elias, thanks for the amazing talk. Just a quick questions. Could you briefly explain what information theoretic generalization bound is and recommendations on some references on the topics?
Yep, that's a grand question. So, okay, second, the recommendations. Yes, there. Sadly, I didn't put this here, and I'm a bit embarrassed that I should have this prepared. But there was a big review paper that came out a few months ago. So I have the feeling if you just put information theoretic generalization bounds on Google, hopefully you'll get like a big paper, like an archive, like a big book that looks at these things. Otherwise, I can send this review afterwards to Bang and maybe he can forward it or something. So I'm just saying there's a relevant reference for this that I cannot give you right now.
I put it in the chat, Elias.
Okay, awesome.
The reference, yeah.
Carlos put it in the chat. Thank you, Carlos. That's very kind. And what's an information theoretic generalization bound? Well, it's a bit of a more like zoomed out perspective, but a priori, one thing you could look at is at the mutual information. Like if you look at your inputs as random variables and as the outputs, like as the labels as random variables, then one thing you can ask is, what is the information, the mutual information between the inputs and the outputs of your model? And with this, like with the mutual information, the way you define it regularly, you can write down a nice looking generalization bound. The problem is that the mutual information is a quantity that you usually cannot evaluate because it requires access to a whole distribution again. So like you're just circling around the problem, but not solving it. But then what you can do is rewrite this mutual information in terms of other things. Like there's something called the change of measure, where they look at a different information metric, and then the approximation quality, like, because in the end, okay, sorry, I'm just saying a lot of things without saying much. There's this new approach that if you start from the mutual information between like the input and the output random variables, then you can find a bound on generalization, on the generalization gap. And this is specific to the function that you chose at the end, like at the end of your training algorithm. And this has a problem that the mutual information, although it's like a very clean mathematical quantity, it cannot be evaluated in practice. So then the game becomes, okay, how can I replace the mutual information for some approximate quantity that approximates the mutual information and which I can actually evaluate efficiently. And then there's a trade-off between, like, the better your approximation is, the more difficult it will be for you to evaluate, and the easier it is for you to evaluate. By information theory, the farther away, like the worse your approximation is going to be. And I think, yeah, right now I don't have much to say other than this, but like so this paper that Carlos put in the chat, we're reading it at the moment, and it seems like it's just a very interesting thing. So if anyone is also reading it or wants to read it together or something, you can just let us know, because it seems like a treasure trove. I'm not sure it will have like easy, clear, direct applications to quantum machine learning, but it seems like the new spin on classical machine learning. So it's just good to be aware of it, I would say.
Cool.
Sorry,
Yeah.
I cannot answer better.
Yeah, but thanks for the reference anyway. I think it's definitely be helpful for the audience to kind of go and read the state of the art in like classical machine learning in terms of like information theoretical generalization bound. So we do have another question from Joseph. Hi, Elias, I'm Joseph, but today my microphone does when talking about quantum measures, do you think all these quantities can be understood from the point of view of information theoretical quantities such as quantum mutual information, divergent, etc.? I guess we can understand all this problem as quantum classical channel.
I think that's an awesome question. Thanks, Giuseppe.
Yeah.
The thing is, I don't have a specific idea in mind when I talk about quantum complexity measures. Like if you ask me, pointing in my head, okay, tell me what one such thing could be, then yes, I would say the quantum mutual information. And this is nice because it relates to this like information theoretic generalization bounds. And I know there is at least one paper that looks at the quantum mutual information, or yes, I think, by Leonardo Banchi, which I put it, sorry, a lot of clicking. And I'm just gonna say that you can look at that paper because it's nice. Whoa, it's very far away. This one, generalization in quantum machine learning, a quantum information standpoint. So thing is, I don't know super much about this, all the different metrics of quantum information, quantum mutual information, and how they interplay with one another. So I can just say this will probably be a good place for you to satisfy your curiosity. And hopefully once we've read this new book that came out, I'll be able to answer you better.
Hi, Elias. Can I ask a question?
Yes, please.
Yes, thank you very much for the very, very clear and very organized talk. So I have a couple of questions on the details of the experiments that you ran. In particular, so I understand your sampling or your data sets primarily consist of states from the cluster, the 4 phases of the cluster, the generalized clusterizing model. So basically, so the first one is, do you do like a 4+ classification supervised learning problem, or do you?
Yeah,
I mean,
exactly.
or
Exactly what we do.
Okay, so it's a 4-class. So basically, in your QCNN, you wouldn't. You would have to at least measure 2 qubits.
Exactly. That's exactly what we do. We measure 2 qubits.
Okay, so that's fine. And the second one is which optimizer do you actually use, and if there is actually a difference in the performance of the cost function where you, because you, as you said, you could get the cost function to go all the way to 0. I guess I don't think 0 probably like some very small number.
Yeah, sorry, like, okay, 2 things. I start from the end. When I said we could get the cost function to 0, here I was when I meant the classification accuracy. So we could like the classification error. So we could bring the training error to 0 in terms of the classification error, but this is important to mention. And on the optimization algorithm, maybe Carlos can jump in and say more, but it was like a genetic algorithm that does crazy things.
Yeah, it's called the CMA. It's a genetic algorithm, basically. We didn't, if I remember, we didn't try any gradient-based algorithm, because at the end we didn't care about the time it took to optimize. We simply wanted to have the best function that approximates the training set. So that's why we use this genetic algorithm.
I see. So I guess if any optimizer is up, then I guess so you would say that the CMA is generally performs fast and better than, for instance, like Covella or any of the SciPy methods. Or
I'm not sure if faster, but I mean, because the landscape very likely is not flat, right? So
yeah,
I don't know if faster than gradient based, but probably better. Yeah.
I see. Okay, so but this is for the only for the training cost, so or the training prediction error. Whereas
no, sorry. This is important. Like, we trained using a regular loss function, but for the experiment results, we plotted the training error. Like
I see. So when you say 0 is a 0 prediction error, but the cost function itself is actually not 0.
Exactly. Yes, and the thing we use to train is the loss function.
Yeah, sure. Yes, that's right. Yeah, because
but it's easier and cleaner to plot the error.
I see. Okay, yeah, thanks. So I will give this CMA a try. I think because in practice I have looked at training different VQCs or even the QCNN, various type of detailed differences in the circuit, and we've never seemed to be able to get a perfect prediction. There's always some small error even in the prediction for the training data. So yeah, maybe this genetic algorithm works. Yeah, because I think I also share the concern that Bing rose about when you go to largest training sets, and so that's my experience as well. With typically we train, we've looked at cases with definitely more than 20 training points, and yeah, in those cases it's very hard for perfect fitting, perfect prediction on the training. You will start having errors that's kind of unavoidable, and so in that sense, this generalization bounds don't quite apply for those settings when you cannot really get a very, very small error for the training.
What I would say then, so like as you say, like this is also what we would expect. If we plotted for higher training set sizes, then the 3 curves would start going down. And notice here we're plotting the generalization gap, which is the difference between the training error and the test error. Right. And like we know that by construction, the test error, in particular for the blue and orange lines, will always be constant up here. Yeah. And so if these curves go down, it's partially because the training error stops being 0. Yes. And at some point, if we get to very, very large training set sizes, what will happen is that the training error will not be better than random guessing, and then we'll have a 0 generalization gap. And with this, what I want to say is, what you described seems like you have a problem where you don't have the best generalization to start with, because you don't have, like, well, no, that's not.
No, yeah, it's more because once you get to larger training set sizes, even if you use a very, very powerful expressive kind of PQC, the trainability issue starts to come in. You might not get to the global minimum, or you might be stuck in the local minimum during optimization. So that's why the optimizer problem also comes in, and how good the optimizer is able to reach the actual global minimum. yeah,
Yes.
it's a real factor now. But
Yeah,
for
then the only
small,
thing would be sorry.
sorry.
No, go for it.
Oh yeah, so as I was saying, but for small training sets, small training sets, then this issue is less of a concern, and it's more likely that you get to converge.
Yes,
and
and here,
I guess this is what you should. Yeah.
And here, what I would like, the only thing is like, then I would make a distinction between the task you're trying to solve and the task we're trying to solve. Like the task you're trying to solve is really go to higher sizes and just figuring out, okay, what's the best performance I can achieve here. Whereas our task is more, we look at who has reported very good performances and then study those cases in our randomized way. So if you're lucky in your endeavors and by this time next year, you beat this generalization performance even for larger models with more set sizes, then we might have to rerun our algorithms, like our tests, with your newfound models that generalize.
I see. So basically, what you're saying is that what these cases so what you found for these successful cases are also using small training sets. I see.
Sorry. Yes, this is very important. I thought, yes. So in this paper by Matthias Caro, like it's, I have it somewhere. Let me find it. The reference. This. In this paper, they report good generalization performance for very few training data. I mean, that's on the title. It's called like generalization in quantum machine learning with few training data or something like that.
See, I'll have a look at it. This is also very important. Yeah. Thank you very much.
Yeah, pleasure.
Okay, yeah. I think it's like now we just like over time. Yeah, there are a lot of good discussion over here, and thanks everyone for their very interesting questions. And yeah, I think we can wrap up our seminar now. And thanks again, Elias, for the very amazing talk. And looking forward to see you in the future in our seminar as well.
Yep. Thank you for having me. It was a great pleasure, and I'll see you around.
Yeah, thanks. See you.